Hello Year 12 and welcome to the third in our live lessons on transition metals and their chemistry. What we're going to look at today is stereoisomerism in coordination complexes. So in the first couple of lessons we've already looked at the chemistry of the D block and what a transition metal is, and also we've looked at ligands and how they form dative or coordinate bonds to a transition metal center and the different types of ligands that we're likely to encounter, such as mono and bidentate ligands. What we're going to move on to today is looking at how the ligands bonding to this metal center can give rise to stereoisomerism in these complexes. And to do that, we're going to find out what a stereoisomer is, remind ourselves of where we've seen that before in organic chemistry. Then we're going to identify and draw cis-trans isomers in transition metal complexes, before finally having a look at how we can identify optical isomers, which is a type of stereoisomer you may have heard of before, but we probably haven't studied. So without any further ado, let's begin. Before we go any further, it's important to make sure that you can recall the key terms that we've looked at and learned so far in this module. So just pause the video for a moment and write out a definition from memory for what a transition metal is, what a ligand is, and what coordination number is. When you've done that, unpause the video and see if they match up to what I write down. Pause the video now. Okay, so transition metal, the first of our definitions, is a metal which forms at least one ion with a partially filled d orbital. So remember, this is why scandium and zinc by definition aren't transition metals, because when they form their ions, they don't form partially filled d orbitals, unlike most of the rest of the elements in the D block. But the transition metals aren't limited to the D block. It's any metal which forms at least one ion with a partially filled d orbital. What about ligands? Okay, so a ligand then we would define as a molecule or ion that forms a dative or coordinate bond to a transition metal. So these could be simple molecules like water or ammonia, where they donate one of their lone pairs to form the dative bond. You could have ions such as chloride. Also get things such as bidentate ligands such as ethane diamine, where the two nitrogens on there can form a coordinate bond each. And then finally, coordination number is defined as the number of dative or coordinate covalent bonds to a transition metal in a complex ion. So remember, the coordination number is the number of bonds formed to the metal center, not the number of ligands. That's a very common mistake that students make, and it costs marks. Right, let's move on and start looking at stereoisomerism. So, again, what I'd like you to do here is just think for a moment about what a stereoisomer is, and what then or how then you can define cis-trans isomerism and optical isomerism. How are these going to be defined, and what examples can you think of for cis-trans, certainly from our prior studies? So what is a stereoisomer, and then what examples have you got for a cis-trans isomer? And after that I'll talk you through what an optical isomer is in a bit more detail. So pause the video now and write down your definition for me, please. So stereoisomers have the same structural formula but a different arrangement of atoms in space. We're familiar with seeing these when we've looked at alkenes in our organic chemistry studies. It's very important in organic chemistry. But complex ions, such as those formed by the transition metals and ligands, can also show stereoisomerism, where the complex ions have the same structural formula but a different arrangement of atoms in space. So what we're used to with cis-trans is something like this. So if we take an example here, if we go for CH3, CH, CH, CH3, which we could name as but2e. So if we draw these out, we should see that there's two possible isomers. We could have here a trans isomer, where the alkyl chains are on opposite sides. We could have the cis isomer, where the alkyl chains are on the same side. So this is where we see cis-trans isomerism in organic compounds. It's a similar concept in complex ions, but with some slight tweaks, which we'll look at in more detail when we get there. Now, optical isomerism is where a molecule or a complex ion has two mirror image forms. And these mirror image forms are non-superimposable. So if you hold your hands out in front of you, you can see that they are mirror images of each other. But whatever you do, you can't exactly place those hands on top of each other in the same conformation. They are non-superimposable mirror images. And we see this in organic chemistry. We see this with things such as seashells. Hands, they form what are called enantiomers, where you have these non-superimposable mirror images, or enantiomers. And that's what gives rise to optical isomerism. And we'll have a look at how that arises in complex ions as well. Let's move on and make a start on this. Now, the first example of stereoisomerism we're going to look at is cis-trans isomerism in square planar complexes. So we have here two square planar complexes. You can see we've got, represented by blue, bonds going into the page, and these black wedge bonds are bonds coming out of the page. Now, we can see here, where you have two of the same ligand on the same side, that is cis isomerism. So over here we have a cis isomer, and you can see that's because they've got things on the same side, that is cis. Where the same ligands are opposite each other, so for example this chloride and this chloride are opposite each other, that is trans. So in a cis isomer, the cis stereoisomer, the ligands that are the same are on the same side of this square planar complex. And when they're trans, they're on opposite sides in this square planar complex, with a bond angle of 180 between them for the trans, and a bond angle of 90 between them, 90 degrees between them if it's cis. Now you have to know how to represent these isomers in an exam. You need to be able to represent them in the normal 3D representations. So underneath each of these, I'm going to draw out the correct 3D representation. And what I'm going to do is draw the cis one out first, and I'd like you to pause the video before you have a go at drawing out the trans one and checking against mine. So for the cis one, I'm going to start with my central atom here of the complex ion. So there is the Cu, and then I'm going to have going into the plane a chloride, going out of the plane I've got another chloride there, then another wedge bond, trying to make sure that there's an angle of 180 between this ligand and this chloride here. There's going to be an ammonia. Now it's the nitrogen lone pair that's bonded, so make sure you draw the nitrogen next to the bond, and going back into the plane like so, the second ammonia ligand. Now what's missing off of these representations are charges. So at this diagram at the top, we should hopefully know that copper tends to be 2+, whereas the chlorides here are minuses. So the overall charge on this complex ion would be 0. So that's balanced out as a neutrally charged compound. So actually what we'll see here is that this is neutrally charged, but to show that it's a complex ion, we'll just put our square brackets around it, like so. Now you guys have a go at drawing out the trans isomer of this square planar complex for me, please. Pause the video, have a go. How did that go? Hopefully you got something that looks something like what I've drawn down here, where you can see you've got this 180 degree bond angle between the opposite ligands, and that the identical ligands, so in this case the ammonia here, are opposite each other, and also the chloride ligand here is opposite each other. So you see how this is stereoisomerism. Both of these complexes have the formula Cu NH3 Cl2. So that's the formula for the complex ion there. They have the same structural formula, but they have different arrangements of their atoms in space, and this can lead to differing properties. And you denote this actually, so this is an important point. So if you wanted someone to draw a cis isomer, you'd write cis in front of this. If you want to draw a trans isomer, well, then you'd write trans in front, like so. Okay, so moving on, we'll have a look at how this cis-trans isomerism arises in a octahedral complex. Okay, so there's our trans isomer. You can see there that you've got the identical ligands which are opposite each other across that complex ion. So what we'll the cis isomer look like? Could you have a go at drawing that now for me, please? Pause the video and check back in a moment when you've done. Right, so here we go. Starting again with that central copper ion, we're going to have our bond state in the plane. So here's going to be chlorine or chloride. Down here we're going to have the ammonia, making sure that it's the species with the lone pair that's bonded to the metal. Out of the plane, we're going to have our ammonia here, and going into the plane, we'll have a chlorine or chloride. Going into the plane over here, opposite that ammonia, we'll have another ammonia, and then down here, our last ligand, the ammonia again, cis stereoisomer. So this is the cis stereoisomer, and this one over here is the trans. Don't forget your square brackets yet again. Now these are stereoisomers, which show cis trans stereoisomerism. Now this is present with both monodentate and bidentate ligands around these complex metal, within these complex ions. So what I want you to do is just review this very quickly, and then join me again for the next video in this playlist, where we're going to have a look at bidentate ligands and how this can then also give rise to optical isomerism in transition metal complex ions.